Hello everyone, and welcome back to this series on single variable calculus. Today we're going to be continuing our exploration of infinite series and also finite series, and talk about one of the applications that they have to finance. So suppose somebody pays you $5 at the end of every month for 8 years. How much is this series of transactions worth today? So what exactly does this mean? So you might be thinking, okay, well, 8 years, multiply that by 12, and then multiply that by 5. That should be equal to how much is this worth today. But keep in mind, as time passes, the value of money definitely changes, and usually one of the structures that we use to quantify that change in value over time for money is what we call interest. So let's suppose that I is the monthly effective interest rate. And you might be thinking, what exactly is a monthly effective interest rate? So in short, and there's more fancier, more formal terms in the finance world, but this is pretty much the rate for which money increases in value over time. So if we draw a little timeline to sort of view how pretty much our money is changed in value over time. So we have 0 months, 1 month past, 2 months past, 3 months past, and so on. Obviously, if we have some balance S0 and we have some balance S1, obviously S1 should increase in value with respect to S0. So if it increases by I%, then obviously to go from S0 to S1, that's going to be equal to 1 plus I. For example, if you have $5 and it increases by 5% in a month, then you multiply that by 1.05 for increasing by 5%. So we can say in formula form that S1 will be equal to S0 times 1 plus I. We can also do the same for going from S1 to S2, and we would obviously multiply by 1 plus I again. And then we can see that S2 will be equal to S1 times 1 plus I. But S1 also has an equivalent representation because S1 is equal to S0 times 1 plus I. And we also have that 1 plus I from that S2 equation. So we can clearly see that this is equal to S0 times 1 plus I squared. So we can actually go directly from S0 to S2 by multiplying S0 by 1 plus I squared. So this 1 plus I obviously is going to be a constant that's going to come up in a lot of our calculations. So there is an abbreviation that is used for 1 plus I, and usually it's going to be alpha. So let's assume that alpha is equal to 1 plus I. And some people will refer to this as the periodic or monthly periodic accumulation factor. And it quantifies the value that the transaction accumulates in value over some fixed period of time. So using the little pattern that we see here, we see that S2 is equal to S0 times 1 plus I to the power of 2. So obviously that little subscript and that superscript will match, and you can use an induction that Sn will be equal to S0 times 1 plus I to the power of m, or equivalently, Sn is equal to S0 times alpha to the power of m. And this is a very, very important equation. But we're not moving money into the future. We're trying to see what those future transactions are worth today. So we need to move them back into the past, into our present day. So instead of moving forward with alpha, what we're going to do is we're going to increase another notation, nu, which is going to be equal to the reciprocal of alpha. So you should be able to see by this definition that if we do nu times alpha, we're going to get 1. And also nu to the n times alpha to the n will also be equal to 1 as well. So using this equation from above, you should be able to see that we can actually go from Sn to S0 using this nu constant instead. And this nu has a name. This is sometimes referred to as the periodic discount factor. The periodic discount factor. So what exactly does the periodic discount factor and periodic accumulation factor do? So we have 1, 2, and 3. So we move one step by alpha, we move one step by alpha, we move one step by alpha, or we can move 3 steps forward in time with alpha cubed. Or we can go backwards, and we can go backwards with nu, backwards with nu, backwards one step with nu, or we can go backwards 3 steps with nu cubed. So that's pretty much the timeline perspective of how we can move money through time to sort of see what those values are equal to. So let's get back to our original motivating example. Let's assume that some person pays you $5 at the end of the month for 8 years. So let's draw a timeline to sort of quantify what's going on there. So we have 0, 1, 2, 3, all the way down to 12 times 8, which we should know is 96, and one time period before would be 95, and so on. So this is going to be our timeline that's going to summarize all of our transactions, which some people call cash flows. So we have $5 here, $5 here, $5 here, $5 here, $5 here, $5 here, and $5 here. Keep in mind that this first $5 is associated to that first month, and this $5 is associated to the last month in that series. All right. So we have this particular timeline, so we have this sequence of 5, and we need to figure out what is the value of this sequence at t is equal to 0. So we need to move this 5 back once, and PV is going to refer to the present value of the sequence. So our first is going to be equal to 5 discounted once. And then we're going to have this, which needs to be discounted twice. So we're going to have 5 nu squared. And we're going to have this one, which needs to be discounted 3 times. So 5 nu cubed, all the way down to the very last one of 5. And that's going to be discounted 96 times. And we clearly see that this actually simplifies because every single term has a 5 in it. So PV is equal to the size of that level cash flow, or that level transaction, because they're all equal to 5. And then we're going to have nu 1 plus nu 2 all the way down to nu to the power of 96. All right, so once we have this, now we can write this in series notation because we have several identities for that. So we have 5 times the sum from k is equal to 1 to 96 of nu to the power of k. So we have this finite series ranging from 1 to 96, and we should know a closed form representation of that. So that's going to be equal to 5, so our base here is nu. So this is going to be equal to 1 minus nu on the denominator, and then nu minus nu to the power of the upper limit plus 1, and plus 1 obviously would be 97. So we have this particular expression, but notice we have a nu in common with the numerator, so we can equivalently write this as 5 times nu all over 1 minus nu times 1 minus nu to the power of 96, and that would be the present value of that sequence of cash flows. Now, before I introduce an interest rate and actually get a numerical value or a monetary value on this present value, I just want to notice something very, very neat. This constant, nu over 1 minus nu, can actually be simplified quite nicely because, remember, nu is 1 over alpha and alpha is 1 plus I. So this is 1 over 1 plus I all over 1 minus 1 over 1 plus I. And then I can get a common denominator with these two fractions by multiplying top and bottom by 1 plus I. And then I'm going to have the same denominator in each of those expressions. So what I'm going to have here is 1 over 1 plus I all over 1 plus I minus 1 all over 1 plus I. These 1 plus i's will cancel, and also these 1's will cancel, and we're just going to be left with 1 over I. So we have that nu all over 1 minus nu is just simply 1 over that effective interest rate, right? And this is very important identity in the realm of finance. So that means our present value from before can be simplified quite nicely as 5 over I times 1 minus nu to the power of 96. All right. So now let's get a particular number. Let's assume that the monthly effective interest rate, so this is going to be monthly, is going to be equal to 0.25%, which is a decimal of 0.0025. So therefore, the present value of this sequence of $5 cash flows over the next 8 years is going to be equal to 5 over 0.0025, so 5 over I, times 1 minus nu, which is 1 over alpha, and alpha is 1 plus I, which is going to be 1.0025 to the power of 96. And once you actually do that calculation, you're going to come out to approximately $426.27. So under this particular interest rate, if you want to purchase this particular sequence of cash flows today, it is worth $426. So obviously, if you want a good deal, you would pay less or lend this person less than $426, roughly. Let's do another example. Suppose that somebody asks you to lend them $20,000 in exchange for $130 at the end of every month for the next 5 years. If the monthly effective interest rate is 0.31%, is this a good deal for you? So all we need to do is figure out how much is this sequence of $130 equal to today and see if it is greater than, less than, or equal to $20,000 and then decide from there. So let's first off draw a little timeline to sort of see what our cash flows are looking like. So we have 1, 2, 3, all the way down to. So we're going to 5 years. So 5 times 12 is going to be 60, and the penultimate month will be equal to 59. So what we have is cash flows of size 130. So 130 there, 130 there, 130 here, 130 here, and 130 here, and obviously 0 there because this 130 is the end of the first month. And we just need to figure out what is this sequence of cash flows equal to. So the present value from the formula that we got before is going to be equal to 130 divided by I times 1 minus nu to the power of n, where n in this case is going to be equal to 60. So I'm just going to put this in generic form. So here I is equal to 0.0031, and then nu will be equal to 1 over 1.0031, and n will be equal to 60. So this is going to come out to approximately $7,107.54. So this is how much it is today. So this is today's value. Versus our $20,000, right? So we're paying them $20,000 for something that's worth $7,000 today. So this doesn't appear to be a good deal. So this is not a good deal for you to take. Now, things in the realm of finance are usually not this easy. You just compare two numbers and then decide from there, but some people do. So if we look at this particular present value, where PV is equal to, let's assume C is the size of each of those cash flow payments. So it's C over I times 1 minus nu to the power of m. One mathematical property that you should be able to see is that as I goes closer to 0, p-value actually gets closer to infinity, right? Which is actually pretty interesting. And that should be obvious from that leading fraction. So that means if you anticipate, interest rates to go down over the next 5 years significantly, maybe this is a good deal. Question mark. Because keep in mind, right now under the current interest rate guess, we're at $7,100, but we still have a long ways to go to get to $20,000. So even though interest rates might go down, it's probably not going to make up that difference. So it's like, okay, well, instead of the next 5 years, what about 10 years? Can you pay me $130 for the next 10 years? Obviously, that will make it a little bit more worth my while. Or what about this interesting question? What if this continues on forever, right? Instead of n equals 5 years. So usually when you have a sequence of cash flows that continue for a finite number of time or a finite number of periods, we usually refer to this as an annuity. And if it continues on forever, i.e. n equals infinity, this is sometimes referred to as a perpetuity. So a perpetuity. So we have that our annuity for 5 years is not really worth our transaction, but what if we transfer this into a perpetuity structure? Will it be worth our time then? So our present value formula will again be equal to 130 times nu plus nu squared plus nu cubed all the way up to nu 60, but now we're going to go 61 and we're going to go all the way up to infinity. So when we write this in infinite series form, that's going to be the sum from k is equal to 1 to infinity of nu to the power of k. Now remember that nu is equal to 1 over 1 plus I, and I is greater than 0. Therefore, this object is in between 0 and 1, which means this series converges because it turns out to be a geometric series. So it's a geometric series whose base is in between minus 1 and 1, and hence it converges. And moreover, since it converges, and keep in mind it's a base point of 1, not 0, that's going to converge to nu all over 1 minus nu. Right? So that's going to be what it is, but keep in mind, nu over 1 minus nu is just the same as I, so this is actually equal to 130 over I, and once you substitute our particular interest rate, this is going to be equal to $41,935.48. So notice that we've jumped from 7,000 all the way up to 41,000, and obviously that's going to make you happy, so the value of this deal actually increased just by turning it into a perpetuity deal. But do you mind waiting quote unquote forever for you to kind of break even with this transaction? Maybe not, but at least you do have some options to decide upon. So let's consider this slight variation of our problem. Let's assume that our payments of size C, so they're still level payments, are made every Q months instead of every 1 month, until time t is equal to q times m, so a multiple of the periodicity of our payments. So instead of 1 month, now we're getting paid every 3 months, or every 5 months, or every year, or every 2 years. That reoccurrence is not as frequent because when we lend some person some money, they have to make some transactions in that time, and it might be really, really difficult to do that within a month. So you give them a year and then ask them to pay you at that particular period. So there are some financial advantages of why you may want to do it. So in our particular example, we're going to be letting q is equal to 3, so what would our timeline look like? So if we start at time t is equal to 0, and then 1, 2, 3, 4, 5, 6, 7, all the way up to, and we're going to go all the way up to q times m. So this is going to be a multiple of m, or q, and in particular this is going to go to 3m. So what does our transactions look like? So we have 0, usually, 0, 0, now this is going to be equal to c, and then 0, 0, c, 0, 0, all the way down to c. All right, so there's our non-zero cash flows at time t is equal to 3, 6, all the way down to 3m. So what would that present value be? So if we write that in series form, that's going to be equal to c times nu to the power of 3, nu to the power of 6, nu to the power of 9, all the way down to nu to the power of 3 times m, or m times 3. And notice that this is equal to 3 times 1, this is equal to 3 times 2, this is equal to 3 times 3, and that's obviously 3 times m. And that pretty much sets us up for a smooth transition into series form. So we have c times the sum from k is equal to 1 to m of nu to the power of 3 to the power of k. Right? So notice that our base now is nu cubed, and our base for our series is k is equal to 1. So we actually know exactly what this is equal to. So this is going to be equal to c times, and it pretty much has the same exact structure as before. So it's the base minus the base to the power of m plus 1 all over 1 minus the base. All right. Notice that we can factor out a nu cubed out of the top, and that is going to turn into nu cubed all over 1 minus nu cubed, and then we're going to have 1 minus nu cubed to the power of m. once we simplify. So that's going to be our present value. And I want to do something very strange at first. I'm going to multiply top and bottom of this by alpha cubed with emphasis to multiply by that fraction. Because alpha cubed times nu cubed is going to be equal to 1, both here, and then alpha cubed is going to be present where that 1 is located. So our present value will just be equal to c all over alpha cubed minus 1 times 1 minus nu to the power of 3 times m. So that's what our present value structure is for every 3-month payments until time t is equal to 3 times m. It's very easy to see that this 3 and that 3 is the periodicity of those cash flow payments, so we can easily generalize this as follows. So the present value will be equal to c, if it repeats every q month, that's going to be alpha q minus 1 times 1 minus nu to the power of qm. So that is going to be our present value structure. All right. So now let us go back to our example, and let's assume that our cash flows C are going to be equal to $50. And let's assume that our time T is equal to N. Let's assume this is equal to 5 years. So it's going to be 5 times 12, which is going to be equal to 60 months. So if we look at our timeline, what are we going to have? And let's also assume that we're paying $50 every 3 months. So we have 0, 1, 2, 3, 4, 5, 6, all the way down to, let's say, 57, 58, 59, and 60. So we're paying $50 at 3, $50 at 6, $50 at 60, and $50 at 57, and we're paying $0 everywhere else. I guess we're not really paying anything, but we can say we're paying $0. So what is that going to be? So from our relation that we just built, our present value is going to be equal to 50 all over alpha to the power of 3 minus 1, and then 1 minus nu to the power of what? Keep in mind, this 60 is the same as 3 times 20, right? So it's going to be m payments of size C that reoccurs every q months, right? Which still goes down to 3 times 20, which is 60, right? So pretty much that 1 minus nu to the power of n stays the same, just like our repeat every month style. The only difference really is instead of this being I, which is alpha plus 1 minus 1, now it's alpha cubed minus 1 instead. So if we take our I to be equal to 0.31%, then this is going to come out to approximately $908.40. Obviously not a lot of money for our 5 years, but what if we turn this into a perpetuity instead? So if this is a perpetuity, which means that n is equal to infinity, which means nu to the power of 3 times m is going to go to 0 because m is going to go to infinity because 3 times m equals n, and n is going to infinity. So that's going to go to 0, so that means this is going to completely vanish, and 1 minus 0 will be equal to 1. So that means our present value for our perpetuity will just be equal to 50 all over alpha cubed minus 1. So if you don't think $900 is a lot of money, well, will this be a lot of money? Well, once you actually work out the calculations, this is going to come out to $5,359.71. Obviously a lot, I guess a lot more than $900. So if you do decide to lend somebody money and they agree to pay you $50 every 3 months forever, make sure you purchase that or lend them less than $5,300 in order to make this worth your time. So those are some of the applications in the realm of finance that you definitely can solve using series and infinite series. Hope you enjoyed this video, and I'll see you in the next one. Take care.